Hey guys, and today I'll be looking at proof by induction. And if you're not familiar, this is a method for proving mathematical statements or formulas, and it's quite popular. And today I will be showing you how it is used and what it entails. So first of all, let's start off with the general method. So proof by induction is pretty simple. So the first thing you do is you prove the rule or the statement for the base case. And for example, this varies from different rules or statements that you make. So let's say your statement that you're trying to prove is that n cubed plus 2n is divisible by 3, for n being part of the positive integers. So your base case is going to be n equals 1 because that's the first positive integer. So you go ahead and you prove that for n equals 1. Now it may not be 1, but in this case it is because we're looking at the positive integers. And then you make an assumption that this case is true for n equals k. So then you say that k cubed plus 2k is divisible by 3. And this is your assumption. You know that this is true. And then going off of that, what you are left to do is prove that this statement is also true for n equals k plus 1. And then once you have proven that, then the whole statement is true and the whole rule is proven. So this is basically the procedure. Now let's look at the example and let's look at why this makes sense. So if you prove the base case, you know that one case works. And you have an assumption that a case k works. So then once you prove that k plus 1 works, you can continue going. And let's see what I mean by that in just a second. But first, let's do an example. So here we will be proving that 1 cubed plus 2 cubed plus 3 cubed plus blah 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 plus n cubed. So the sum of all positive integers up until and including n cubed is equal to n squared times n plus 1 squared over 4 for any n that is a positive integer. And go back to this process and try to prove this yourself, or just watch me and follow along if you're not feeling too confident yet. So the first step is proving for the base case. And here, like I've already said before, our basic case is going to be n equals 1 because n has to be a part of the positive integers. So the sum of 1 cubed until 1 cubed is just 1 cubed, so it's going to be 1. And then according to this formula we have, it's going to be 1 squared times 1 plus 1 squared over 4, which is just going to be 1 times 4 over 4, which is just going to be 1. So this has the same answers. So therefore, we have just proven the base case. Now, we have to make an assumption. So our assumption is that for n equals k, the rule is true. So the sum of 1 cubed plus 2 cubed up until k cubed does equal k squared times k plus 1 squared over 4. So we know that this right here is true. Now what we're left to do is to prove the case of k plus 1. But be careful because proving k plus 1 will look differently. And in the end, we're not going to have this formula because if k plus 1 is our value, then we're going to be trying to prove that the sum of the cubes up until and including k plus 1, which is what this symbol means, this is the same as the pattern over there, is equal to not k squared, but we're going to have k plus 1 squared, and then we're going to have k plus 1, which is going to be equal to k plus 2 squared over 4. Because once again, our n is k plus 1, so this would translate into this expression instead. Okay, so let's start proving. So what we're trying to prove is that 1 cubed plus 2 cubed plus 3 cubed plus etc. plus k plus 1 cubed. Now, what's important to recognize is that we make this assumption for a reason. We do it to help us. So we always try to find a way in which we can substitute this into the expression right here. So in this case, we're going to quickly recognize that in between these numbers, before k plus 1 cubed, there's a k cubed, and then we add a k plus 1. And right here, recognize that this is exactly what we have made an assumption about. We know that this is for sure equal to this expression right here. So now we can rewrite this as k squared times k plus 1 squared over 4 plus k plus 1 cubed. And then we can further work with this to have k squared times k plus 1 squared plus 4 times k plus 1 cubed over 4. So now we're working with the same denominator. And now we can factor out k plus 1 squared. So we're going to be left with k plus 1 squared times k squared plus 4 times k plus 1. All of that over 4, right? Because we can write k plus 1 cubed as k plus 1 squared times k plus 1, right? Simple exponents. And now we can simplify this right here. This is going to equal to k plus 1 squared times k squared plus 4k plus 4 over 4. And this is going to equal to k plus 1 squared times k plus 2 squared. We're just factorizing this expression right here over 4. And would you look at that? This is exactly what we were trying to prove right here. Because if k plus 1 is our n, then this translates to n squared, n plus 1 squared over 4. And we have proven our rule for the case of n plus 1. So now, based on induction, we can say that since we have proven the basic case, and since we have proven the case of n equals k plus 1, this rule is true for all cases, and we have just proven it. And let me quickly, before I end this, tell you why it makes sense. Well, think about it. You have a base case that is proven. So once you have your base case, you take your base case, and you say that your base case is equal to k, right? And then you have proven that the formula is true for k plus 1, right? So you translate your base case and you know that the next case is also true. But now because you know that this case is also true, you can add on another case. So your k plus 1 is going to turn into your n. And you know that n plus 1 is true. So you know that the next case is also true. And you continue going like that. And that's why it makes sense intuitively. So I hope you enjoyed, and I hope you got a gist of how this works. Keep referring to these 3 steps. It's actually very simple. The most complicated part is navigating around proving the case of k plus 1, because sometimes you need to simplify or expand algebraic expressions, and you might get a bit lost. And don't forget that usually, or always, for k plus 1, you'll be trying to prove a formula that looks slightly different than your standard formula, because here n is equals to k plus 1, and I strongly recommend plugging in k plus 1 and identifying what it is that you're proving first before you actually prove. Alright, so I hope you enjoyed, and I hope you learned something new. Have fun practicing, and see you next time.